Hi there, welcome to GeeklyEDU Chemistry. My name is Sona Singh and today we are talking about nuclear reactions. First, we know what's a reaction. Something is going to react and turn into a product. The main difference between a chemical and a nuclear reaction is nuclear reaction create new events and it involves nucleons, that's neutrons and protons, and the energy involved is much more. And it is not influenced by external factors. We already know this from high school biology, right? Now, first of all, why will some element undergo nuclear reaction, right? So when we plot a graph between atomic numbers and mass numbers, what we find, the n by p ratio is pretty important. And as we go, the mass numbers increase too much. So if the neutron to proton ratio is more than 1, specifically a number around 1.3 is found out, then we say that the element is radioactive. It lacks stability and it will emit some particle to become stable, to achieve nuclear stability. Now, what is the energy that might be needed for the same thing? So we calculate a binding energy which tends to keep neutrons and protons together. The way to calculate binding energy is by calculating the mass deficiency, that is the sum of all electron, proton, and neutron masses, and subtracting the actual mass of the atom. The mass deficiency near about comes to be 0.15. And as long as there's a mass deficiency in the atom, there'll always be energy associated with it, which we call as a binding energy. This comes from the Einstein's famous equation E equals mc squared. In this case, E is delta mc squared. Now let's first calculate delta M for chlorine. I'm going to take a pause and I want you to solve for yourself. Now let's try to crack this. So number of protons, that's 17 multiplied the mass of a proton. Number of electrons, that's again 17, again multiplied by the mass of an electron. That's all in AMU. And again the number of neutrons, that's 18 in this case, and again multiplied by the mass of the neutrons. You do the total calculations and then we sum this up, that this comes to be around 35.290. Now, if you subtract that from 34.9689, you get your delta M. Now, you could be asked how to calculate the binding energy. Take a pause and do it. So the delta M, I hope you did, is AMU. You converted that into gram per mole, which comes out to the same amount, numerically speaking, and then multiplied by C squared. C is 3 into 10 to the power 8, and that comes out to be 2.89 10 to the power 10, right? So if you supply this much energy, which is equal to about 76,000 kgs of water boiling from 0 to 100 degrees. So you see why radioactive processes are energetically demanding. So radioactive decay is to bring the N by P ratio into the stable region, right? So if it's outside, you want to bring it into the stable region. How do you do that? By kicking out neutrons or protons, or by some way even electrons sometimes. So there are three types: alpha, beta, and gamma. The general types. There are more and we'll talk about them briefly. So these three types of decay differ in, let's say, the first thing, that is charge. So alpha is, and if you talk about beta, that is just like emitting out an electron, so a -1 charge. Gamma has got no charge, it's just electromagnetic energy. The mass of alpha is definitely, that is of He2 plus particle, 6.64 into 10 to the power -24. Beta, that's about of that of an electron, and gamma again, it's just energy. Now alpha, because it has got mass, hence it will have very less penetration amount. So if you compare, then alpha is, if it's 1, then beta is 100 and gamma is 10,000. So you can see gamma radiations are really doing bad. They will penetrate the tissues and harm us to the most extent, right? So that is why gamma rays are the most harmful ones. Now let's take some examples of these decays. So radium, that's 226 upon 88, decays to Rn plus alpha particle. Rn was radon, by the way. Now iodine decays by beta to xenon and gives out an electron. Now gamma radiations, we do not generally write these equations because we know there's nothing, no change in mass atomic number going to happen there. right? Now there are other kind of decays. Now positron is just the opposite of an electron. It will have no mass but a positive charge. So carbon decays to boron, and as you can see, there's only the change is in positive charge, right? So how this happens is that this proton decays into a neutron and a positive electron, or positron. There's another way called electron capture. Electron capture, this Rb decays to krypton, right? Now here, what happens is you capture an electron together with a proton, converting it into a neutron essentially. So that is how this electron capture method happens. I hope you could understand the various types of decay. Now let us try to work out on a numerical involving the same. So these are your homework questions. You have to try to solve it yourself. I'll leave the answer in the comments down below. Now, what's the rate of the decay of alpha, beta, or gamma? Now, the rate of decay follows first order kinetics. Now, that means you know that the rate of the reaction is proportional to a single value of A, right? And the K here is rate constant. We already talked about this. I'll leave the link down if you want to revise the rate laws. Now we can write the integrated rate equation, that is ln a naught upon a is equal to AKT. You can also find the half time, that's 0.693 upon K. Now, a very practical example this is strontium, which was liberated during nuclear test, and now we can find them in our bones and teeth because it has a half time of 28.8 years. Now, let's try to solve a few questions. So, cobalt treatments, you know that cobalt, radioactive cobalt, is used for medical treatments to kill cancer cells. It has a half time of 5.27 years. You have to find out to solve how much of cobalt would remain in our body after the treatment. If you consumed or you were given 3.42 micrograms, let's say after 30 years, how much of that is left? Okay, so pause here and try to solve it, and I will wait for you. Okay, I hope you did. So first let's find out what is K. So T half, you already know the formula, 0.693 upon K. T half is already given to us. So we just find out K, that is around 0.131. Okay, now we use the integrated rate equation, which can tell us the leftover according to time. So ln a naught upon a equals kt. We already have K, we have T to be 30 years, right? So a naught is the initial concentration, A is the present concentration, right? And that is 0.131 times 30. Okay, so now we have to do the math. You have to take log of both sides so that we can eliminate the ln. And then a naught upon a, if you do the sum, do the math, comes out to 51. And a near a naught, because we know was 3.42 micrograms, we find out a to be around 0.067 micrograms, right? So this is how they do it. Now here's another problem. You find a rock, it has 0.257 mg of lead for every 1 milligram of uranium. You have to calculate the age of the rock, and the half-life is given, that's 4.5 in 10 to the power 9 years. Try yourself and leave the answer in comments, and I'll explain this in the next video to come. Do check them out to understand the difference between fusion, fission, and transmutation. Thank you so much.
We hope you liked this video. Press subscribe, thumbs up, and stay geekly.